Okay, so for this question here, so background info, this can be, I torque and angular acceleration. I think it's one of the hardest chapters of the year. But what you want when you come across a problem like this that starts talking about torque, what I want you to realize is that torque is the rotational equivalent of linear force. So here's what I'm saying. So if you have an object on a surface and there's a force applied to it, and there's no force to stop this, this block would accelerate, right? Or in fact, let's make there be multiple forces. Let's say we have F1, 10 newtons, and then we got F2, 3 newtons. So the net force on here, horizontally, would be 7 newtons positive. To the right is plus, to the left is minus, right? So 10 wins over 3 by 7. Now, what is net force equal to? Net force is equal to mass times acceleration. Now, mass is it's the measure of linear inertia. And what is inertia? Inertia is the ability of an object to resist a change in motion. And for linear situations like this, the one measure of inertia is mass. So a big giant truck compared to a Prius, the truck is going to have a lot more inertia simply because it has more mass. Now, for rotational situations, so let's say we have a disk, right? So we have a disk and then there's like an axis in the middle. So this disk can rotate. So if we come to this disk and we apply a force, well, yeah, we have a force, but for these situations, we don't want to talk about force. We want to talk about torque. And what torque is the product of force and the perpendicular distance from the axis to the force. So from axis to force, that's D. So the definition for torque is you take the force that's causing the rotation, right? This force would cause the disk to spin, and the torque is going to equal that force multiplied by the perpendicular distance from the axis over to the force. It has to be perpendicular. Now, this torque is going to cause a special acceleration called an angular acceleration. This disk is going to start to spin faster, 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 right? If that torque stayed. So we know that torque net is going to equal I alpha. What is I? I is rotational inertia. So down here, the reason why I'm going through this, in part B of the question, they ask us to solve for the rotational inertia. So I want to give you a way to think about this and understand it. Rotational inertia, it's the ability of a rotating object to resist a change in motion. So basically, the harder it is to start this disk spinning, the harder it is to get it spinning, the greater the rotational inertia. And it works the same way as mass for linear situations. The bigger the mass, the harder it is to get this box moving, okay? Now, rotational inertia, there's equations for it. It depends upon the situation. Generally speaking, for rotational inertia, like if you have let's say you have a ball on a string. So here's a string and here's the center. So like somebody's standing here, here's a kid standing here, like that. And this kid is swinging this ball around in a string. So the mass is at the perimeter. For a situation like this, the rotational inertia is going to be mr squared, where m is the mass of the ball, and then r is the radius of the circle. So generally speaking, all equations for rotational inertia it's some mass times the radius squared. It's going to be some variation of that, but the equations are different. So like for a disk, for a disk like this that's spinning around, what is a disk? I want to say disk, don't quote me, but because my memory is awful, but I think rotational inertia for a disk, I think it's 1/2 mr squared, where m is the mass of the disk and then r is the radius of it. Okay. All right, so let's take a look at this problem, but here's how you want to think about it. You know, connect these torque problems back to linear motion, because the thing to realize, this equation here, and this equation here are really the same equation, but this one is for rotational situations, and this one is for linear situations. Okay, so let's revert this. All right, so we have a disk and it's rotating about the axis at its axle at the center. A student's experiments reveal that while the disk is spinning, friction between the axle and the disk exerts a constant torque. So right in here, right where the axle meets the disk, there's friction in there. There's friction, and that friction is going to cause the disk to slow down. You know, this disk starts with an angular velocity, and the friction there is going to cause this initial angular velocity to get smaller. So the disk will it'll have a decrease in the angular velocity, which, by the way, that is an angular acceleration. If the initial angular velocity changes, the change in that angular velocity is going to be an angular acceleration. All right, so at time t = 0, the disk has an initial counterclockwise. So they're giving us sign convention here. They're saying that counterclockwise is positive, and the angular velocity is omega naught. The disk later comes to rest. So angular velocity final is going to go to 0 at time t = 1. So that's on the graph here, t1. Okay, on the grid at the left, sketch a graph that could represent the disk's angular velocity as a function of time from t = 0 to t1. So as the disk goes from its initial angular velocity to a final angular velocity of 0. All right, so because the torque, we can assume that the torque on the disk is constant. The graph will look like this. So the graph starts up here because we're starting with this initial angular velocity, and we know that the final angular velocity goes to 0, which is going to be here. And if the torque is constant, that's going to be a constant acceleration, which means that this needs to be a straight line going down like that. Okay, and then the angular acceleration is going to be constant as well. It's going to be like this. It's going to be a negative constant acceleration. Now, relate this back to linear motion. Like, let's just do like, so let's say we have a block here it has some velocity, and then it reaches a region that has friction. You know, so like here we have friction present, and this friction is going to be constant. So this vector right here represents velocity. This is v, that's not a force. And then over here, the velocity goes to 0. So if we look at the box, you know, as the box is moving through this region of friction, I'll draw the box again. So again, I can't go back and erase because my tablet doesn't let me do that. This vector is velocity, but if we look at the forces as it slides through this region, we'd have friction pointing that way, and then obviously mg down, and then normal force up like that. But if this friction is constant, the acceleration is going to be constant, because that's the only force that's causing a horizontal acceleration. So if we graphed this, so this right here goes back to one of the first things we did in physics. If we made a graph of velocity versus time, Well, when the box reached this point right here, it has a positive velocity, because let's say to the right is plus and to the left is minus. It has a positive velocity, and then over here, that velocity goes to 0. And if you remember back to kinematics, a velocity time graph, the slope of this is acceleration. And the reason why is on a velocity time graph, rise over run. So what is this rise right here? That rise is the change in velocity. What is the run? That's the time. And that happens to be the definition for acceleration. You're like, oh, slope is rise over run. This rise is change in velocity. The run is time. Change in velocity over time is acceleration. So the slope is the acceleration. So if we go to the next graph, which is this one here, so now we want a graph of acceleration versus time. Well, from this graph, what do we notice about the slope? Well, the slope is negative, the slope is negative, and the slope is constant. It's a constant negative slope, which means it's a constant negative acceleration. This box, as it moves from here to here, the acceleration would be pointing this way, right? Against the motion. So in a very similar way, with this disk, the disk starts with a positive angular velocity, because they defined it, they defined counterclockwise as positive, and that goes to 0. And if torque is constant, so let's write that out. So torque net equals I alpha. So looking at this equation, if the torque on the disk is constant, then the angular acceleration must be constant, which means that the velocity is going to change at a gradual rate, like that. Okay. Let's go to the next part. Okay, next question. No, we want this. Okay, part B. The magnitude of the torque exerted on the disk is that. Derive an equation for the rotational inertia of the disk in terms of the applied torque, the initial angular velocity, and T1. Okay, so all right, so the way we're going to do this is we're going to look at this disk right here, and we're going to say, okay, from what they've told us, there's only one torque acting on the disk. As this disk rotates, there's only one torque, because no other torque was mentioned. So let's sum the torque on that disk. The only torque acting is T naught, and this is going to equal I alpha. Now, alpha is angular acceleration. Let's plug in for that. Angular acceleration is going to be change of angular velocity over time. Change of angular velocity is going to be angular velocity final minus angular velocity initial over t, but angular velocity final is going to be 0 because the disk stops spinning. So angular acceleration can be written as negative angular velocity initial over time. So this is our equation for angular acceleration. Let's plug that in right there. And by the way, if we're calling this acceleration negative, we should also call this torque negative, because the torque is acting opposite what was defined as positive. If the disk is spinning clockwise, the torque is acting, I'm sorry, if the disk is spinning counterclockwise, that means the torque must be acting clockwise, the other way. So this is going to be a negative torque. So now we have negative T naught equals I. Alpha is negative. And then this is T1. because T1 is the time it takes to stop. The negatives drop out, and now we can solve for I. The rotational inertia is going to be that. Okay, so that's part B. Okay, part C. Okay, part C. So in another experiment, the disk again has an initial positive angular velocity at t equals 0, and then at t equals 1/2 t1, the student starts dripping oil on the contact surface between the axle and the disk to reduce the friction. As time passes, more and more oil reaches that contact surface, reducing the friction even further. Okay, let's go back to the first image. What's happening here is oil is being added right there, which is it's gonna reduce the torque that's causing the disk to slow down. If the torque is reduced because oil is added, so torque equals I alpha. So if we reduce the torque, if that torque goes down, is that going to change the rotational inertia of the disk? Would the rotational inertia of the disk change? Would this change? The answer is no, because the rotational inertia of the disk, it depends upon the mass of the disk and the size and the radius of the disk. So this is not going to change. Rotational inertia won't change. So if the torque goes down, rotational inertia stays constant. So therefore, the angular acceleration must decrease, which simply means that the angular velocity is not going to be changing as rapidly as before. It's going to be a more mellow change in that angular velocity. So that's kind of the setup for this situation. Okay, so what would this look like? Well, the oil was added at 1/2 T1. So what would happen is, so we start with our positive angular velocity, and the angular, it would look something like this. So the angular velocity is going to change at a constant rate, straight line, something like that. So this should be constant slope. Then when the oil starts getting added, the angular velocity is not going to change as rapidly as before. So it's going to, the slope is going to kind of mellow out. It's going to kind of go like this. In fact, maybe let's go to like here, a little higher up. So straight line like that, and then the slope is going to go, it's going to curve like that. Okay, so for this first region, this is going to be a constant angular acceleration. And then for this next part, the angular acceleration will decrease. Now remember, on a velocity time graph, like we said earlier, the slope is the acceleration when you're on a velocity time graph. So just think of what's happening to the slope. So right here, the slope is like that. There's slope. And then you go a little, then come right here. Now the slope is like that. And then come right here. Now the slope is like that. So that shows that the angular acceleration is decreasing. Why is the angular acceleration decreasing? Well, because the torque is decreasing. All right, and then as far as our angular acceleration goes, so we're just gonna take what we did here. The way we go from this graph to this graph is by looking at the slope again. So let's look at the slope. So for this first part right here, constant negative slope. So you're going to do something like this, constant negative slope. And then what's happening here? Well, the angular acceleration is actually getting smaller. So at a gradual rate. So the angular acceleration is changing. And it's not necessarily going to reach zero. In fact, maybe draw it like this. It doesn't need to reach zero. Okay, last part. Okay, these questions, they give us equations and they want us to know if these equations make sense. When I first read this, I had to be honest, I had to make up specific numbers. What I did when I read this, I was like, okay, so let's just say that T1 is 2 seconds. And so therefore 1/2 T1 would be 1 second. And then something in between would be like 1.5 seconds. So use real numbers here to get this clear in your head. Okay, so the student's trying to mathematically model the magnitude of the torque exerted by the axle on the disc when oil is present between, let's see, at times greater than 1/2 T1. So the student is looking in this region right here. The student is looking from 1/2 T1 to T1. The student writes down the following two equations, each of which includes a positive constant C1 or C2 with appropriate units. So the equation is for torque. So let's first figure out what happens to the torque. In fact, let's go back real quick to the previous. When oil gets added between the axle and the disc, what is happening to the torque? The torque is going down. You know, it's the rubbing of friction between axle and disc is going to become less, which means torque goes down. So what we're looking for here, what we're looking for in these equations is an equation that shows a decrease in torque in this region from 1/2 T1 to T1. The equation that does that is this equation. And again, I recommend using numbers. In the first equation, let's just plug into it. So let's say that T is let's say that T right here is 1.5 seconds. So I'm going to write this down. So torque equals the constant T minus 1/2 T1. So let's just say that this T, let's say we're looking at 1.5 seconds. That's the moment in time where we're looking, okay? Just because T is a variable. And then 1/2 T1 would be 1 second. So this would be torque equals 1.5 seconds minus 1 second. Well, that's going to be the constant multiplied by 0.5. So this would be 0.5 C1. So let's now look at 1.8 seconds. Let's look a little bit later. 1.8 seconds. So now change this to 1.8. 1.8 minus 1. So now the torque went to 0.8 C1. So what we're finding here is as time goes on, the torque seems to be increasing, which does not make sense. Whereas in this equation, if you do the same thing, so torque equals C2 T plus 1/2 T1. So let's do the same numbers again. So first, let's do 1.5 seconds. So this would be C2 over 1.5 plus, so 1/2 T1. If T1 is 2 seconds, that would be 1 second. So this would be C2 over 2.5. Now what happens when time goes by? Let's look at a little bit later, 1.8 seconds. This would now become 1.8 plus 1. So that's going to now become C2 over 2.8. So we're seeing here, as time goes by, the torque is getting smaller because the denominator is getting bigger. So which equation better mathematically models the experiment? Definitely equation 2. Briefly explain why. What you're going to say is because in equation 2, torque is decreasing from 1/2 T1 to T1. That's really all you got to say. Okay, questions on this? Okay, if there's no questions, let's go to the last one.